Hi everyone, my topic is inverse Galois problem. There are two parts of my presentation today. First, I'll talk about the inverse Galois problem statement and related examples. Then I will walk through the important milestones in inverse Galois theory. So first, the inverse Galois problem, let G be a finite group and let F be a field. The inverse Galois problem, as formulated for the pair GF, consists of two parts. First part is a general existence problem. So determine whether G occurs as a Galois group over F. In other words, this problem concerns the determination whether there exists a Galois extension L over F such that the Galois group Gal of L over F is isomorphic to G. Now, if such a field L exists, we say that G is realizable over F and L is a G extension over F. The other part is called actual construction. If G is realizable as a Galois group over F, construct explicit polynomials over F having G as a Galois group. More generally, construct a family of polynomials over F having G as a Galois group. The classical inverse problem of Galois theory is the existence problem for the field F equals to Q, which is the field of rational numbers. This is the base field that we will be focusing on in this presentation. Recall that we have learned and proven in class that if F is a finite field, or F is a field of Q elements, for example, then every extension L over F is Galois, and the Galois group of Gal over F is always cyclic. Let's look a little bit at small groups. So there's this proposition that all groups of degree smaller than or equal to 15 occur as Galois groups over Q. Let's look at this table of a few groups of order from 1 to 8. They can be categorized into abelian and non-abelian groups. We see there are a few non-abelian groups, so D6 for order 6 and D8 and the quaternion group Q8 for order 8. Let's first focus on the abelian groups. So I think this proposition may be helpful. Let's review it a little bit. This is a proposition that we have proven in problem 3, homework 10. Let n be a positive integer. Let zeta n be the primitive nth root of unity, i.e. zeta n to the power of n is 1 and zeta n to the m is not 1 for any integer m that is bigger than or equal to 1 and smaller than n. Let Q adjoin zeta n be the splitting field of this polynomial fx equals to x to the n minus 1. Then Q adjoin zeta n over Q is a Galois extension, and the Galois group is isomorphic to the units of Z mod NZ or Z mod NZ cross. Now let's look at this table. So the idea is that we will, for each group of each order, we will find a minimal polynomial, and then find the splitting field of that minimal polynomial, and the Galois group of that splitting field over the base field is isomorphic to the group of that order. So we can see that it's straightforward to see the minimal polynomial of the minimal polynomial we're interested in is fx equals to x, and then the splitting field would be Q itself. Then the Galois group is just consists of the identity function 1. And then the proposition that I've shown above is useful in the case of the abelian group of order 4. So we see f of x is x to the 5th minus 1, and then of order 6, as we can see in this polynomial. So we have proven in problem 2, homework 9, that the minimal polynomial for the abelian group of order 3 is f of x equals x cubed plus x squared minus 2 of x minus 1. And then we've shown in class that the Galois group of the splitting field of this polynomial, f of x equals to x to the 4th minus 10x squared plus 1, is isomorphic to this group, Z2 cross Z2. So we have built some, we've realized some abelian groups of order 1 to 6, so actually all of them in this slide. So the motivating question is that how can we generalize this? How can we do that for other groups of bigger orders? So let's look at a more specific example first. Consider n equals to 7. We know that the group Z mod 7 Z cross is 1, 2, 3, 4, 5, 6. H equals to 1, 6 is a subgroup of this group. And we want to let K be the field fixed by H. Then we have this correspondence by the fundamental theorem of Galois theory. So we know that the order of G mod H is 3 because of the orders of G and H, and then correspondingly, K, the field fixed by H, the order of Q over K is 3. We claim that K is equal to Q adjoint theta, where theta is zeta 7 plus the 7 to the power of 6 is actually the field fixed by H. Then the minimal polynomial of theta over Q has Galois group of Gal of K over Q is isomorphic to Z mod 3Z. So the idea is to have a big group, and then we find a big field, and then we find something in the middle. So in this case, we find something in the middle that is isomorphic to the group Z mod 3Z. Now let's generalize that a little bit. So let n equals to p to the power of alpha for some prime p. We consider the Euler-Toscan function phi of n is equal to the size of the group Z mod nz cross, and this is equal to p of alpha minus 1 times p minus 1. If alpha is 2, then this Euler-Toscan function is just p times p minus 1. So we substitute alpha into this function, and then let h be a subgroup of order p minus 1, and let k of q adjoint theta be the field fixed by h. We have a very similar tower as we've seen on the previous slide. So p on the previous slide is 3. So we can see that the minimal polynomial of n theta, minimal polynomial of theta over q has Galois group of gal k over q is isomorphic to Z mod pz. So we conclude that every cyclic group of prime order is a Galois group of some field extension, which is pretty interesting. So for all finite cyclic groups, what we can do, so first we have some group that we want to realize it as a Galois group, right? So Z mod capital NZ. Then we factor n into powers of primes and pick a bigger n, let's denote it like small n, a bigger one, compared to capital N, which is also a power of primes of P1 all the way to P of n. Then P of n is this, n times P1 minus 1 times P2 minus 1 all the way to P of n minus 1. Then there exists a subgroup H of Z mod NZ cross with the size of H is this. Then let K be which is a subset of Q adjoint zeta n, be the field fixed by H, which is a subset of G. Then K is a simple extension where K is Q adjoint theta for some theta. And the minimal polynomial of theta over Q has Galois group that is isomorphic to Z mod NZ. So we have realized that is the way that we realize a finite cyclic group. Now we can actually generalize it to all abelian groups. First, let's look at the fundamental theorem of finitely generated abelian groups. So let G be a finitely generated abelian group, then G is isomorphic to Z to the R cross Z and 1 all the way to Z and M for some integers R and 1 and M, satisfying two conditions. The first condition is that R must be bigger than or equal to 0, and then n of j is bigger than or equal to 2 for all j, which are integers between 1 and m, and I plus 1 divides ni for all integers I between 1 and m minus 1, and this expression is unique, right? So we have this isomorphism that is helpful. Then the Kronecker-Weber theorem actually states that any finite abelian group G occurs as a Galois group over Q. Now, indeed, G is realized as the Galois group of a subfield of the cyclotomic field Q adjoint zeta, where zeta is an nth root of unity for some natural number n. Now, there were, so for the example that we did earlier, the theta, so K is equal to the field in between in the tower. K is equal to Q adjoint theta, and theta can actually be constructed using Gaussian periods, which is a certain kind of sum of roots of unity. I have a few more milestones that may be interesting. This one, Shavarevich proved that every silver group occurs as a Galois group over Q. One thing is that this argument is not constructive. So that is the end of my presentation in some bibliography. Thank you very much for your attention.